assume that the limit of a function as x approaches a number, any number, exists, and let's denote it by L. Also, the limit from g of x as x approaches a also exists. It can be the same number, but let's say it's a different number, m. So without this assumption, the limit laws do not exist. Here's the first limit law. Number one, limit as x approaches a from either side. It can be from the left or from the right, the same thing. From f of x plus g of x. What do you think this equals to? A wild guess. I don't want you to say distribute this operator to these two functions. I don't want you to say that. But that's the idea. So the limit of a sum is the sum of the limits. The limit of a sum is the sum of the limits. But no, we are not distributing the limit operator to these two. I like to present both. If this is a difference, of course, this will be a difference. I like to put them together. And of course, this is L and this is M, so I'm going to write L plus or minus M. And I want an example here. Let's say the limit of x plus 1 over x as x approaches 0. My question to you is, according to this limit law, can I write the limit of x plus the limit of 1 over x as x approaches 0?
Yes, according to the law, yes.
So the assumption was that the limit of the first piece exists, and the limit of the second piece, the second function, exists. This is a limit of a polynomial function. How much is this? We discussed how to determine the limits of a polynomial. What is this? How much?
Wouldn't, if we plug that in, we get 1 over, is that a 0?
So we're talking about the limit of this.
Oh, just the x, I'm sorry.
So what is this limit?
0?
Yes.
0.
0. 0 is a number. This exists. But now let's talk about this one. I need to refresh your memory on how to graph 1 over x. This is a very important function. Please remember it forever so we don't have any issues. So we don't have to go back and graph it all the time. So what is the limit from the left of 0 for this function?
Negative infinity?
The limit from the left of 0 is negative infinity, and the limit from the right of 0 is?
Positive infinity.
Good. So what will be this limit then?
Does not exist.
Yes. Therefore, we are not allowed to use the limit law, because the limit of the first one exists is 0, but the limit from the second one does not exist. So the assumption is extremely important. If the limit of this and the limit of this, if they exist, then we can write this. But if one or both limits do not exist, we cannot use the limit law. What limit law? That says that the limit of a sum is the sum of the limits, or the limit of the difference of two functions, or more, is the difference of the limits. Because this one in our example exists, but this one does not. Is this clear?
Can you do that again, please? Say that over.
I'm sorry?
Can you repeat that over, please?
Which part?
The last part.
So the limit of the second function does not exist.
Mm-hmm.
So in other words, this does not exist. The assumption is not fulfilled.
Right.
So that's why we cannot use the limit law.
Okay.
We can use the limit law only if both limits exist. This one is 0, but this one does not exist. So I cannot break the limit from here. They are not the same. I cannot apply the limit law and say that the limit of the sum is the sum of the limits. It cannot. It doesn't work because this one does not exist. The requirement is that both exist. And one of them does not.
Mm-hmm.
Very good. Moving on to the second one. Okay, so we have in number 2, we have the limit of a constant times a function as x approaches a. What do you think this will, common sense, what do you think? This is a constant, the factor in front of f of x. Any wild guess? Anyone?
Mm-hmm.
Would we multiply the limit by the constant?
Yes. C times the limit of f of x as x approaches a. Since we denoted this by L, so this will be C times L. Number 3.
Sorry, can I just clarify? So when you're using the capital L is representing the limit of f of x.
This is how we denoted it. If you don't want to use capital L, just use W. It doesn't matter. It's just a letter that we used from the beginning to simplify. It doesn't matter. These don't matter at all. We just use the letter to just simplify the final answer. You can use W and Z, and then this will be CW. It doesn't matter, whatever the L is, whatever the quantity is. It's just for simplicity. Is that what you were asking? Is that okay?
Yes.
Okay, very good. The next one, limit of f of x times g of x as x approaches a. Any wild guess for the answer? The limit of a product will equal the anyone?
The product of the limits?
Exactly. Limit of f of x as x approaches a. Limit of g of x as x approaches a. And since we denoted this by L and this by m, it's just L times m. Perfect. Number 4. Limit of f of x divided by g of x as x approaches a. Wild guess? It's not that wild. Anyone? What do you think?
Would it be L over M?
Yes, But we have to write limit of f of x for everyone to see, of course. And limit of g of x approaches a, it is indeed L divided by m, only if, I never said only if in any of the other situations, but I have to say it now. And why do I have to say only if? Can anyone tell us why I have to say only if something, something, something?
Is it only if m does not equal 0?
Exactly. Or in other words, limit of g of x as x approaches a does not equal 0, of course. It will be undefined. The whole thing goes away. Great job. Thank you. Number
Even
5.
if, sorry, what if they were to both be 0? Or is that other case that we're not talking about yet?
So yes, so if they're both 0, if they're both 0, which is this case, there is hope, but I have no idea what the result would be, and we have not discussed this yet.
Okay.
Yep. So the denominator cannot be 0. But if the numerator is 0, the answer is 0. Okay. So limit of a constant as x approaches a. What do you think? A limit of x as x approaches a. I don't call these limit laws, but they're common sense. But the book calls them limit laws. That's fine. So what do you think this is? If there is a... Of course. Who cares where x is going? C is also C. Always C. The limit of x as x approaches a. Since this is a polynomial, how did we just discuss? How do we determine the limit of a polynomial? What will be the answer?
We would plug in whatever a is.
Good, that's it. I plug in a. Whatever a, but I plug in a. Good. What about the limit of x to the nth power as x approaches a? Again, I don't call this a limit law because this is a polynomial. So what will I write as the answer? So n positive integer. So what is the answer now? It's the same case. There is no difference here.
A to the m.
That's it. Yeah, I'm sorry. My n has 2 bubbles and my m has 3 bubbles. Sorry about that. N or m, it doesn't matter. Same thing. Okay. Number 8. Limit of the nth root of a. I'm sorry, of course, x. When x approaches a. What will this equal to? It's the same thing. No changes. It's just that there is a root. So a is positive for n even. So what would be the answer? They're all the same. All these 3 are the same.
A.
That's it. Good. And now the last 2, let's say 9 and 10, are quite similar. And I just wanted to talk about them because they will come back a little bit later. And I'm going to call them the swapping of operators. We're going to use them this property later. It's a very important property, swapping the operators. So here's the explanation for 9 and 10. So the limit as x approaches a from f of x to power n, and the other one, let me put them both here, as x approaches a from the nth root of f of x. You can say what's different? Yeah, it's the same thing, but we're talking about the function now, not just plain x. So when we look at this concept here, this is the first operator. So to the function, I have to raise the function to this power and then apply the limit. So this is the inner operator, the first one, and this is the second operator. Well, I can swap them. I can make this one the first operator, and I can make this one the second. So I swapped the order of the operators, or I swapped the operators. This was number one, this was applied second, but now this is number one and this is applied second. And of course, this will be f of a to the nth power, right? Or since we know that this is L, it will be L to the n. Even better. Let me put it and stick with the assumption from the very beginning. There is no need for that. It's the same thing, but it's better to do that. So we swap the operator, but I have to mention that swapping the operators requires a condition that we haven't talked about, but I will put it here because it's important. Under conditions or condition of continuity, which we will talk in the next section. So for now, just remember this: the swapping of the operators is allowed only if everything is continuous, and we will discuss that. Same thing here. This is the first operator, this is the second operator. I am allowed to swap them. The nth root of the limit of f of x as x approaches a. And this is L, so then the answer will be the nth root of L. So, of course, we have to assume that n is a positive integer here, n positive integer, and of course here the function has to be positive, because otherwise I can't take the nth root if n is even. So the swapping of the operators will be discussed a little bit later in chapter 3. So basically, keep this in mind, that the inner operator can become the outer operator can become the inner. And of course, the same thing here. Okay, enough of that. Let's look at a couple of examples. I hope I'm not logged out again. Please. Please.